So the big deal about the ideal gas constant is to use an R constant. Then R, it's a number and a bunch of units. So here comes my R. I'm going to write it in blue so you can see it. We're going to talk in this video about the ideal gas law, which is really one of my favorites. So first of all, let me just get to Avogadro's law. Avogadro is the guy that gave us the number of particles in a mole, right? Avogadro's number. So that's how you can remember moles. So it's interesting that equal volumes of gases at the same conditions have equal number of moles, equal number of particles. And so let me just illustrate it like this. Let's just say I have a certain volume and pressure and temperature. I will have equal number of particles in each balloon. So I have a mole of helium, and one thing I know here, if I have a mole, I have the same number of particles, right? The same number of molecules or atoms. But what would be different about each of these? Well, a mole of helium would be 4 grams, a mole of oxygen would be 32, and a mole of CO2 would be 44 grams. Isn't that interesting? Equal volume, temperature, pressure, moles, different masses. All right, let's get to the ideal gas law. So you recognize pressure and you recognize volume and of course temperature, but we have a couple new variables. So N stands for number of moles. So that's where Avogadro comes in, a number of moles. And then R is what we call the ideal gas constant. And that is a constant used in the ideal gas law. And there are a couple different values for R. One that I like to use is the 0.0821 liters atmospheres per mole Kelvin. Now that's a lot of units to go with that number. You may see different numbers that have different units. Units that match the pressure unit of your problem. So let's just do a problem here. Before we do that, let's explain the difference in real and ideal gases. So an ideal gas is just what you think. Ideal. It would have perfectly obey the ideal gas law. It would have perfectly elastic collisions. Particles would never attract each other, and it has zero volume, the gas particles. Now, generally, gases behave ideally. Zero volume, the collisions, they don't lose energy, and those particles don't attract. So you can just imagine all these little particles, boom, 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 not losing energy. However, under certain conditions, and you need to know these conditions, gases become more real, meaning the volume becomes significant. They do start to attract one another, and they do slow down when they collide. When does that happen? Well, that is at low temp, and you think about what happens at low temp. They're moving very slowly so that when they collide, they might actually attract each other. And then high pressure, that means they get smashed really close together. So close together, moving slow, gases might start to behave more real and attract one another than ideal. Okay, here is our ideal gas law problem. First of all, let's identify what's given in the problem and the variables. So I'm looking for volume. I like to put V equals question mark. And then I've got, ooh, that's a mass. What am I going to do with that? I bet you I can convert that to moles, right? And then I have a temperature. So let's go ahead and convert to Kelvin by adding 273. Remember that. And then I have a pressure. Okay, so I'm going to write my equation, PV equals nRT. And I'm going to solve that for the variable that I want. I'll solve for volume by dividing by pressure. Now, before I start to plug things in, let's get our number of moles. So I'm going to take my 24 grams of oxygen and convert that to moles. So I know that 1 mole of oxygen is 32 grams, And so 24 grams is 0.750 moles. Okay, so that is my N. All right, so now I have N. Now, one thing that I am going to use is the R that I gave you, 0.0821 liters atmospheres per mole Kelvin. Now, my pressure is not in atmospheres, so let me go ahead and fix my pressure here. So I'll take my 86 kilopascals, and I know that 1 atmosphere is 101 kilopascals, and so that will give me 0.856 atmospheres. Okay, I think I'm ready. I'm going to plug everything in. So here we go. Number of moles, 0.750 moles. Okay, and then R, it's a number and a bunch of units. So here comes my R. I'm going to write it in blue so you can see it. 0.0821 liters atmospheres per mole Kelvin. Okay, and then here comes my temperature times 298 Kelvin. I'm going to go ahead and erase this just so you can see the problem here. And then on the bottom, I'm going to divide by my pressure, which I just calculated, 0.856 atmospheres. Okay, remember I took that to atmospheres. All right, now this looks like a mess, but watch this. We're going to cancel out some units. Don't skip writing the units in these problems. So I have moles on the top, moles on the bottom, atmospheres on the top, on the bottom, Kelvin, Kelvin, and I'm left with 1 unit and a bunch of numbers. And I'm left with liters, which is perfect. So all I need to do is gather up my numbers, this times this times this divided by this, and I will get 21.4 liters. And that is a good example of how you use the ideal gas law.